So in the last two videos we talked about relations and functions, and now it's time for us to classify them. So let's start with a definition. Let's take a function f that goes from the set x to the set y. Now we're gonna classify, so we say f is, and here is our classification. So the first one is injective. We say f from x to y is injective if for every element x and x prime in x, so I'm taking elements from my domain that verify that f of x equals f of y, then we have x f of x equals f of x prime. We have x equals x prime. So let's view this as a Venn diagram. I think it's very visual and very important to know how things work in a picture. So this is gonna be my set y, and I'm gonna have the set x here and arrows going on here, but I don't care how my function works in this side, in the side of the axis, because I already know it's a function. In the other videos we used to draw this side when we were trying to decide whether the relation was a function or not. Now we already know f is a function, so f is a function. Okay, so I want to see how do the elements in x behave knowing this hypothesis in y. So what I do is I have a few elements in here, and I'm gonna draw some arrows representing my function. So I'm going to say that an arrow comes from down here, goes there, another one comes like this, and I'm just gonna draw a straight line here. So I know that this element has this function, this f of x, this element has this one, and this guy has this other one. I didn't define it for this one, but it doesn't matter because it's a function if for every element here we have one arrow for each and not two arrows going from one element. So this is a function. And is it injective? Well, I have to check two elements that verify this. Well, in this case is somewhere very clear, maybe because f of x is different than f of x prime for every x and x prime in x. So let's view this. It's easier actually knowing when it's not injective. So let's draw another set. We have this set y, and like this. What I'm gonna do is, okay, let's say I have my x here, and let's suppose we have like this and one other going from down there. So this is f, this is x, x and x prime, two elements from x, and they both have the same function. So this element, this one, would be f of x, and it would also be f of x prime. Now the way I drew this, we know that x is different than x prime, because if they were the same then it would be only one element. So I have two elements with the same f and they're different. So I have two elements here. The f acts the same way in both of them, but they're different. Oh, well, they should be the same if the function were injective. So in this case, this one is not injective. So this is the definition in the first classification for functions, so injectivity. Now the second one, f is surjective. F, I'm going to write it again, f goes from x to y to z, and f is surjective if for every element y in y there exists at least one x in x such that f of x equals y. Okay, so again, let's draw our Venn diagrams. This is my set y, and here would be my set x, and I have a few elements. And again, I'm going to draw how the function works with arrows. So let's say I have like this. And a straight line. Now, what I have to do in this definition says for every element y in y. So what I'm looking at is this set. I'm checking the elements here, and all these elements must have an x that verifies that f of x equals y. So I start with this guy, and I say, well, yes, because I can follow this arrow and it takes me to this element x. So okay, this guy is fine. Now when I move to the second guy, to the second element in y, there is no arrow. So for this, let's call it y1, I have that there is no x in x such that f of x equals y1. Oh, well, that's a problem because I needed to find one. Then this is not surjective. It's not. Let's draw an example of a function that is surjective. So you have that one clear. Again, I'm going to draw my set y and a few elements. Now, we saw in the last example that when an element here has no arrow, then it's not surjective. So it's easy then to know that if I have an arrow in each of these elements, then my function will be surjective. So if I draw like this, here I would have a problem with this one, but okay, I will define it like this. Now this one, this f, is surjective. And this is, I can take any element. I'm going to start taking elements and checking if there's an arrow coming from an element in my set, my domain x. As all these elements have an arrow, then this function is surjective. Now, the last classification is bijective. So function is bijective if it is injective and surjective. Okay, and the only way these Venn diagrams can be drawn is, well, it has to be injective, so every element that has the same f has to be the same in X, so each element would have to go to a different one. So we will have this, and no other element here can take this spot. It's like students and seats. So each student goes to a seat, and once they sit, then that seat is taken. No one can sit on top of that student. So the same would happen here. I need every element in my domain to have a different element in the image. Now, if I look at this, I say, okay, this is injective, but it's not surjective. It's injective, but it's not surjective because this element has no one. So in this case, this wouldn't be bijective. So for it to be, I would have every element in Y to have only one element here. Okay? So bijective is the sum of injective and surjective. Let's view this with a few examples. So I'm going to define a function. My function is f that will go from the set of the natural numbers to the set of the natural numbers. And I'm going to define it as f of n equals n plus 1. Let's think about injectivity. First, injectivity, and if it were injective, then I have to take f of n. So I take n m in my domain here, and I suppose that f of n equals f of m. Now, what does f of n mean? Well, it means n plus 1. And the same for f of m is n plus 1. Now, if I subtract 1 from each side, then I would have n plus 1 minus 1 equals n plus 1 minus 1. Oh, well, that's n minus 1. And if I start doing calculations, these elements go, and I have n equals m. Oh, well, that's really good, right? Because I have f of n equals f of m, and from this I was able to conclude n equals m. So it is injective. Okay, so that's great. Now let's take the surjectivity and try and say whether this function is or not surjective. So what I have to do is take an element here and check if there's an element here. Now let's start with the first element, 1. Well, 1 belongs to n, to this one. And I wonder, is there n in n? This n would be my domain. So I take an element in my codomain and I say, is there an element n in my domain that verifies f of n equals the element I took, equals 1? Well, let's suppose there is. So f of n equals n plus 1 equals 1. Now I can subtract 1 from each side, and this gives me that n equals 0. Okay, but the natural numbers, 0 does not belong to the natural numbers. Okay, 0 belongs to the natural numbers with a 0, and this is not the set I have. So this tells us there is no n natural such that f of n equals 1. So for this example, we would have f is not surjective. So f is injective, but f is not surjective. And then we have that f is not bijective. Why? Well, because it's not surjective. I would need both things for it to be bijective. Let's take another example, and very similar. I'm going to say a function g that goes from the integers into the integers, and it's defined the same way I define my f. So no, it's not f, it's g of z equals z plus 1. Now let's think again about injectivity. So injectivity, the same way as before, I take set 1, set 2 in set, in the domain, and I assume that f of set 1 equals f g of set 2. Okay, I'm going to do this better. G. Okay, now let's use the only thing we know, and that is the definition. G of z is z plus 1, so G of z1 is z1 plus 1, and G of z2 is z2 plus 1. Again, subtracting 1 from each side, I get z1 equals z2. So this tells us that f, so because of this we know f injective. Now let's talk about surjectivity. So we have, let's take set in set, but which of these ones is? It's the codomain. And I want to know, I wonder, is there an element k in set here, the domain, that verifies g of k equals set? I'm asking myself this, and I want to find one. If I find one for any set in set, then this would say that my function is surjective. So let's think about a function for a while. Okay, let's suppose there is one. Okay, if there were, then g of k would have to be set, but g of k, my definition, my definition said g of k equals k plus 1. So I'm going to write that because it's the only information I have. So g of k equals k plus 1. And I want to know if this equals set. Well, this is something I don't know. I'm asking myself this. This is part of this question. So I took an element set, and I want to know if there's a k that verifies this. Well, there is. Right? If I take k equals set minus 1, then what I would have is I would have f of k equals f of I continue with f, and it's g, right? I'm so sorry. G of k equals g of z minus 1, because that's what k means. And g of z minus 1 is what I have inside plus 1, and in this case it's z minus 1. So z minus 1 plus 1 equals z. Oh, then I took an element in my codomain and I was able to find an element k that belongs to z, but the set of my domain. I was able to find a number in my domain that verifies that g of that number equals the one I took in the first place. So for this, then what we have is that g is surjective. Now we have that g is injective and g is surjective, then g is bijective. Now this can be done with any function, and I'm gonna give you one exercise. It's pretty simple, and we will work this with more examples in the next video. So a problem. I want you to do the same analysis, so check if f is injective, surjective, and bijective. For f of x, f is going to be a function that goes from the real numbers to the real numbers, and it's going to be defined as f of x equals x squared. So try and do this, and before I close this video, I want to talk a bit about the graphs. So graphs can be very helpful, and I'm going to do the graphs for these two examples. So starting with this one. In this example, what I can think of is my domain. I'm gonna write it as a horizontal line, so this would be n, and my other set, my codomain, as a vertical line. This would be n. Now what I do is I take an element in my domain and I will draw a circle or a point where f of n is defined here. Okay, so let's start with the first element. So this is the number 1. What I do is f of 1 equals 1 plus 1. That's 2. So I come to the number 2 and I say, well, f of 1 equals 2. And I do the same for every element. Now I have 2, and f of 2 equals 2 plus 1, 3. So this is 3, and I would have to put a point here. And as I keep doing this, I end up having lots of points in this direction. And this is the graph of f. Now this graph is maybe ugly because the points are very separate from one another, and that's because both my domain and codomain are the natural numbers, and the natural numbers have these spaces. So what I'm gonna do is, and this might be very helpful for you to solve the exercises, what I'm gonna do is help you with the graph of this problem. So let's draw. Well, as always, we start with the axis. So I would have here the real numbers, this one, domain, and as a vertical line the other set, which in this case are also the real numbers. I'm going to start with the easy ones, right? So I'm going to start with 1. So f of 1 equals 1 squared, which is 1. So I'm going to draw a point in the point of the plane 1, 1. Now when I do f of 2, this is equal to 2 squared 4. So 1, 2, 3, 4. This is a approximation for the graph, but well, it's what we have. I'm going to do it another color. So f of 1 equals 1, f of 2 equals 4, and well, I have no more space, so f of minus 1 equals minus 1 squared, which equals also 1. So when I come to minus 1, I have again a point in there, and f of minus 2 equals minus 2 squared, which equals 4. So when I come to minus 2, then again I would have 4. And this is this point here. Now when I do this for every point here, I end up having a line like this. And this is soft here. Okay, that's awful, but you got the point. So okay, so we would have f of 2 here, and this goes to the infinity, and this is very soft in this corner, so let's fix this is f of 2 and this is 4. Alright, this is a pretty awful graph, but when you do this exercise, try and think about this graph and answer these questions. Well, why is this part? This part would be the real numbers negative. Well, this part has no points in my function. Why is that? In what way does this affect one of these properties? Also think about this. F of 2 equals f of minus 2, which equals 4. How does this symmetry affect me when checking for these 3 properties? These 3 classifications. Sometimes drawing the graph can be the answer to the classification we need. So I wanted to make this clear. Try and solve it, and if you can't, then leave it in the comments and I will help you.